Okay. Great. So thank you very much. It's a pleasure to be here. Thank you for the invitation. So if I can get this straight. Okay. My talk is titled Entropy of Holographic CFTs at Large Charge and Angular Momentum, and is based on the first paper there that's been written and the many other papers that are yet to be written with very optimistic estimated times of arrival. Okay. My talk is going to be divided into 4 parts, excluding the introduction. So let's start the introduction. Okay, given a CFT, the spectrum of operators of the CFT is one of the most basic things you want to know about the CFT. Now, suppose you've got a CFT that has a holographic dual and you're interested in operators at energies of order n square. We know the dictionary to compute the spectrum of operators. What we're supposed to do is to find black hole solutions with the relevant charges in the bulk dual and use the Hawking-Bekenstein entropy formula to compute the entropy of these operators. Okay? And this, of course, has been done, this kind of exercise has been done over the last 30 years. Okay? However, if you were interested in the entropy as a function not just of energy, but energy and charges, angular momentum and other charges, this usual exercise has a well-known problem. And the problem is that the usual black holes that we look at, Kerr ADS black holes or Kerr-Neumann ADS black holes, usually go unstable when their charges become large enough, become near enough to extremality. Okay? And so these unstable black holes cannot represent the dual to thermal equilibrium, cannot correctly capture the entropy of the dual field theory. So this talk is dedicated to the following question: what is the correct set of black holes that captures the entropy of these field theories at large charges where the more traditional black holes become unstable? Okay, so let's start. Let's first look at the simplest class of black holes, the most universal class of black holes that, in addition to energy, have only one additional charge, namely angular momentum. This is a very simple setup because we can study this setup within Einstein, at least to start with. We can study this setup just within Einstein's equations with the negative cosmological constant. Since that's a universal truncation, that's always a consistent truncation of any two-derivative theory of gravity that admits an ADS solution, the answers we get here will be very universal. Will apply to all field theories that have ADS, two-derivative ADS gravity duals. Okay, so as you know, ADS hosts these black hole solutions that have energy and angular momentum. These are called Kerr ADS solutions. And the first question you can ask is, for what range of energies and angular momenta do these solutions exist? Now, before asking this question about black holes, you could ask in a field theory, do we know where we expect operators or states to exist in the conformal field theory? Unitarity tells us that there should be no states with energies below the angular momentum. So right from the get-go, we should expect that there are no black holes whose energies are smaller than the angular momentum. And now if you look at the actual well-known explicit solutions for these Kerr ADS black holes, you find that these black holes exist only in this shaded, orangish region. If you fix the angular momentum that's on the x-axis and lower the energy, you hit a point where below that black holes don't exist. This point that you hit is where the black holes go extreme. Note that the extremality curve lies above the unitarity curve in agreement with the expectations of unitarity. But it's a bit odd. You might find it a bit odd that black holes don't saturate this unitarity. Okay, this sounds okay so far, but there's a problem, a well-known problem. It's been known for over 20 years that any black hole in ADS that has omega greater than 1 is unstable. Okay? Intuitively, you can understand this as follows. A black hole with inverse temperature beta and angular velocity omega, computes a partition function that looks like trace of e to the power minus beta h minus omega jz. Now, look at an operator like del z to the power n, where O is any single trace operator, some fixed single trace operator, and let n become very large. Such an operator has both very large angular momentum and very large energy. But and when n is very large, the energy is approximately equal to the angular momentum. And for this reason, if omega is greater than 1 in equation 1 up there, energy is equal to angular momentum, but omega is greater than 1. So the Boltzmann suppression becomes a Boltzmann enhancement. Okay? And so such operators want to condense if omega is greater than 1. So it's as simple as that. Okay? Now, the important thing is that by explicit computation, you can look at the known Kerr radius black holes and check what the value of omega is. You find that omega becomes equal to 1 on this red curve, becomes greater than 1 on this, in that blue shaded region. So these Kerr radius black holes cannot be stable. Okay? They cannot represent the equilibrium, or they cannot correctly compute the entropy of the field theory. Okay. So what does? What is the end point of the instability of these Kerr radius black holes? What correctly computes the entropy of the field theory? Well, in order to understand this, it's useful to think physically. Let's remember that if you've got a black hole in ADS, it's in equilibrium with a gas. This equilibrium is a dynamical equilibrium. The black hole is constantly emitting Hawking radiation. The gas is constantly falling into the black hole. It reaches some sort of equilibrium. Okay, so the charges of the black hole, the charge resides part in the black hole and part in the gas. Now, normally, if we're interested in large N physics, we ignore the gas, because the energy and angular momentum and everything else contained in the gas is order 1, while the energy and angular momentum and entropy contained in the black hole is order n square. So in the large N limit, we forget about the gas. However, I've just argued that as omega approaches 1, the gas diverges. The energy in the gas, the angular momentum of the gas, and so on, diverges. So certainly, this neglect is unjustified as omega approaches 1. Let's see this better. Consider, okay, I'm going to study the gas, ignoring the presence of the black hole, and in a moment we'll see that this is justified. Consider a particular scalar operators and look at all its descendants. Okay, let's look at the gas made by multi-particling all these descendants. Okay, so this is given by a simple sort of Bose formula. Now these descendants of the scalar operator are can be parameterized by 3 numbers. I'm working at the moment in ADS4. It's the simplest situation. We'll generalize in a minute. Okay, the number of del squares, the angular momentum representation obtained by symmetrizing and making traceless the derivatives, and where in the angular momentum representation you are. How far from the highest state weight you are. Okay, so these are the 3 numbers. N is the number of del squares, L is the representation, and A is how far from the highest weight you are. Okay, so each of these modes gives you a factor once you multiparticle it, a Bose kind of factor. What's important about this formula, equation 3, is the following. The sum over A and N are weighted by beta to the power 2n and beta to the power omega A, and are highly damped. So the sum over A and N only get contributions from small values of A and N. However, look at the sum over L. That is weighted by a suppression factor that goes to 0 as omega goes to 1. So that is the divergence. Okay. Now, in order to quantitatively understand what's going on, as in the limit that omega goes to 1, we can replace that sum over L by an integral and easily convince ourselves that this partition function is some stuff divided by 1 minus omega, has a pole in omega. And because of that, the energy and angular momentum that comes out of this partition function, the energy and angular momentum in this gas is proportional to 1 over 1 minus omega square. However, when you do okay, now you see that when 1 minus omega is of order 1 over n, the energy and angular momentum in this gas is of order n squared, so of the same order as the energy and angular momentum as the black hole and cannot be neglected. Okay. However, it's a simple calculation to check that at those same values of omega, the entropy of the gas is only of order n. Okay, and so can be neglected with respect to the black hole. Okay? Now, notice that I got my dominant contribution to everything from gas modes that had very large L. Gas modes with very large L live at very large values of the ADS radius, and so don't care that there was a black hole in the middle. So though I did the calculation in pure ADS, it's self-consistently justified. Okay, the next thing I want you to notice is that, okay, so just the fact that the gas and the black hole are very far from each other tells you that these two components of our system are effectively non-interacting, very weakly interacting, just because of radial separation in ADS space. You might wonder that when I did this calculation, I pretended that the gas was free. So you know the effect, the back reaction of the gas on the gas. But that is also justified. And one way of understanding this is to check that the density of this gas is very low. And so its back reaction on the gas modes is not significant. Okay? So you can pretend the gas is free, you can pretend that it does not, you can compute it without computing its interaction with the black hole, and you land on your feet. Okay? Now, I've said all this, but we've done this in more detail in this paper. We've written down an explicit supergravity solution for these objects we call gray galaxies. We call them gray galaxies because they sort of remind us of our galaxy. You know, the configuration has a black hole in the middle. It's got a disk of gas. The disk of gas has fixed proper thickness, and it's very large. It's of order square root of n. Okay, the radius of the gas is order square root of n. So n is the parameter that justifies the non-interaction between the black hole and the gas. Okay, and there's one other thing that you might worry about. The thing that you might find unpleasant is that we've found a supergravity solution for this. Okay, the supergravity solution is sourced by the gas. Now the gas is in a thermal ensemble. So because of that, it's not one solution, it's many solutions, actually e to the power n solutions, because the entropy of the gas is n. And you might worry, well, when you find a supergravity solution, for which mode of the gas? Turns out it doesn't matter when n is large, because of the law of large numbers, fluctuations in this bulk stress tensor are suppressed by 1 over square root of n. Okay? And so you can reliably, in the large n limit, find a supergravity solution for this configuration, and we've done all of that. Okay. Now what's the punchline? The punchline is this. If you believe my construction, we now have an entropy formula for S as a function of E and J, for all E and J. And the entropy formula goes like this. For E and J, where the original Kerr radius black hole was stable, that gives you the correct entropy formula. For any other E and J within the unitarity region, choose a point, draw a 45-degree line, and let it intersect this red curve. Okay? Wherever it intersects the red curve is the entropy of the situation. Why is that? Because you see, these unstable black holes decay until they've lost enough energy and enough angular momentum so that the gas is in equilibrium with the black hole at omega equals 1. The gas carries E equals J. That's why it's 45-degree line. Effectively, it carries no entropy. So all of the entropy of our gray galaxy solution lies in the black hole and is given by the simple construction. Okay, so the simple construction gives us the formula for the entropy as a function of E and J for black holes. Okay, one last thing. In this case of ADS4, you can compute the boundary stress tensor dual to these solutions. Boundary stress tensor dual to black holes is nice and smooth. Different black holes with a green, orange, and blue curve. But the contribution of the gas is a delta function at the equator. Not quite a delta function, its size is 1 over square root n. The large n limit, a delta function at the equator, because the gas is going whoosh, pushed out by centrifugal force. Okay, so this is an order parameter for this new solution, this delta function on the equator. Okay, I've talked so far about these black holes in ADS4. You can generalize the story to higher dimensions. The main difference is that there are more angular momenta because there are more cartons for SOD when d is greater than 3. And you have more interesting classes of solutions. These are under investigation. Let's forget about it. Okay, fine. Great. So now we understand what happens at large angular momentum. What about large charge? Is it true that black holes at large charge near extremality also go unstable? Well, in some contexts, this is definitely true, and it's famously true. This was made famous by this paper by Gubser in 2008, which he pointed out that charged black holes sometimes are unstable. Charged black holes are sometimes unstable when, depending on the details of the charged fields outside the black holes. Now, Gubser's instability is simplest to understand when these charged black holes in ADS are small compared to the size of ADS. Well, what happens is that if you've got a mode with charge E and energy omega, and you've got a black hole with chemical potential mu, then in flat space, this black hole exhibits the superradiance phenomenon, which is that if you send some of the mode onto the black hole, what you see is that once it bounces back, more comes out than when you send it. In flat space, superradiance is a phenomenon. In ADS, it's an instability because the mode goes, hits the black hole, back, bounces up the ADS wall, hits the black hole back, and so on. Okay, so Gubser's instability was, for small black holes, is essentially a superradiant instability, and the condition for the existence of this instability was the one I mentioned. Now already you see that this is not such a universal story anymore. You need to know the spectrum of charge fields in the theory to know whether the black hole is stable or not. So now, let's not try to be completely universal. Let's fix on a particular theory. Let's choose our favorite theory, n equals 4 Yang-Mills theory. In n equals 4 Yang-Mills theory, surprise, surprise, the condition for instability, E by delta, the existence of modes with E by delta is greater than equal to 1 is instability. BPS bound tells us E by delta is less than equal to 1. So we are on the edge. Modes that are BPS are on the edge of being unstable. You have to do a little more calculation to check whether they're unstable or not. All this was done more than 10 years ago. And when the dust settles, you find that there is an instability. There's an instability region even in n equals 4 Yang-Mills theory. By the way, I should emphasize that this instability was studied. Yeah, okay, fine. There is an instability in n equals 4 Yang-Mills theory, and there's instability for the lowest chiral mode. Trace x squared plus y squared plus z squared, the field dual to that. Okay, the instability region. Okay, sorry. Actually, this is just where black holes exist, and this. Okay, I don't even have that graph. Sorry. This is where black holes exist, and then there is another curve above that where they go unstable before they stop existing. Before extremality. Okay. So this phenomenon, as I said, was pointed out by Gubser. It's a very simple phenomenon when the black holes were small, but sort of became complicated when the black holes became larger. Because in this situation, you can no longer ignore the interaction between the cloud of stuff and the black hole. And the analysis of these hairy black holes, as they were called back in the day, became very complicated when these black holes became big. It was essentially a subject of numerics. Okay, I described the hairy black holes that were constructed, allowing for condensation of just the lightest chiral mode. Turns out there's a consistent truncation in supergravity that allows you to do this consistently. Okay, so good. So now it's clear that the stories I've told you about angular momentum and charge have some similarities so far, but they also have 2 or 3 key differences. The main difference is this. Okay, there are 2 main differences. First, the angular momentum story involved an infinite number of modes, all modes with large enough angular momentum. Whereas the charge condensation seemed to be triggered, at least Gubser's story, was triggered by 1 mode. Relatedly, the angular momentum story had a very simple answer. Instability at omega equals 1, 45-degree lines computing entropy. Whereas, to get answers for the charge story, you seem to need to do some complicated numerics. Sounds a bit unsatisfying. Now, you might wonder, look, you've got an infinite number of modes also in n equals 4 Yang-Mills, the infinite number of chiral operators. We've stabilized the black hole with just one of them. Perhaps the others are also important. Okay? The stabilization was self-consistent. That didn't mean it was correct. 5 minutes. Okay, great. Okay, so let's go. Do the other chiral modes play a role? Well, there's a very simple argument saying that they do. And the simple argument goes this way. Recall that when charge is large enough, of order n or larger, gravitons blow up into various things. Giant gravitons are dual giant gravitons. The ones that are of importance to me are dual giants. Dual giants become bigger and bigger and bigger. Their radius goes like square root of q, where q is the charge of the graviton in units of n. Okay, so when you take a dual giant with charge which is large in units of n, okay, it becomes extremely big. Okay, and for this reason, you have a situation where a potential configuration, a configuration with a black hole in the center and a giant graviton separated from it very far away, dual giant graviton. Now, because the dual giant graviton separated very far from the black hole, it's not interacting with the black hole. And because the dual giant gravitons obey E equals Q, it's a simple argument that I don't have the time to tell you, but canonical ensemble, it's trivial, that the instability to the nucleation of these dual giants is at mu equals 1, very similar to omega equals 1 before. Now you can go back and look at the construction of these Gupsa-type black holes, and you find that all these Gupsa-type black holes always have mu greater than 1. So they themselves are unstable to the nucleation of these new dual giant gravitons. And in fact, the entropy of charge in the presence of these dual giant gravitons is given by a picture exactly analogous to the one we had for angular momentum. You should draw in the region where mu goes larger than 1, or all the way up to BPS, you can draw this 45-degree line. Wherever you hit the mu equals 1 curve, gives you your entropy. Fantastic. Part 3. Okay. Now, what about when you have both charge and angular momentum? So let's look at a situation, n equals 4 Yang-Mills, with J1 equals J2, Q1 equals Q2 equals Q3. The SO6 cartons equal, the SO4 cartons equal, and energy. 3 charges. Energy E, J, and Q. Okay. Now, in this situation, we've got a 3-parameter set of charges, and there are 4 interesting surfaces. First, the BPS plane. Second, the plane of the surface of extremality. Third, the surface where omega is 1. Fourth, the surface where mu is 1. Okay? I've drawn a constant J slice of this plane here, and you find something nice. You find that all of these 4 surfaces meet at a point in this plane, but that's true at every point for every plane, so they all meet at a line. And this line is the line of Gutowski-Rial supersymmetric black holes. Okay? Everywhere under the black curve is superradiant unstable, and everywhere under the red curve is dual giant graviton unstable. There's no competition, there's no point that is both unstable under both, and so you get a phase diagram like this, where you have normal black holes up there, giant gravitons there, giant gravitons dressed by these duals up there, and you're happy. This phase diagram extends all the way down to the BPS plane. Okay, great. Part 4. In the last 2 minutes, I'm going to tell you about supersymmetry. Yeah, 1 minute. Last 1 minute. Okay, excellent. As I've mentioned above, the phase diagram I constructed has this nice feature that it goes all the way down to supersymmetry. But now you might wonder, is that approximately true at large n? Or is it an exact thing? Supersymmetry is a yes-no question. It's violated by e to the power, whatever. 1 by n squared, it's not supersymmetric. Right? Okay. Naively, our phase diagram descends down to supersymmetry. I claim that our phase diagram actually descends down to supersymmetry. I've given 3 arguments to make this. There's no proof. I'm giving 3 arguments to make the case. First argument. Turns out that if you look at these dual giant gravitons at finite radius, in the presence of a supersymmetric black hole, you can show that at the level of the probe analysis, this probe dual giant graviton is supersymmetric. This was in fact done in the paper by Aroni, Benini, and collaborators. Okay, so that suggests that it's not like some effect that depends on these giant gravitons being very far away. It's an exact thing. Second, there's some evidence that the same is true for gray galaxies. And third, there are other rotating solutions that I haven't told you about, rotating black hole solutions that one can show are exactly supersymmetric. Because all it does is take a supersymmetric black hole and set it moving. Okay, so I know that was fast, but you trust me implicitly, so you should believe that our construction goes down to the BPS plane. Excellent. So now that our construction goes down to the BPS plane, we now have a construction of a 5-parameter set, 5 once we include all charges, of BPS configurations. You know, there's been this nagging irritation all through the study of these BPS black holes. That is, while there are 5 charges other than energy, energy is fixed by the BPS bound, there's only a 4-parameter set of known supersymmetric black holes. Once you take these supersymmetric black holes and dress them by supersymmetric gravitons or dress them by supersymmetric dual D3 branes, you get solutions all over this 5-parameter set. Okay? In particular, when we fix on Q1 equals Q2 is equal to Q, Q3 is equal to Q, and J1 equals J2 equals J, on this plane of J versus Q, there's this Gutowski-Real line that I've drawn here. Anything to the top of that, anything to the top of the Gutowski-Real line is, there's a solution which is a supersymmetric gray galaxy, and its entropy is given by just projecting down onto the Gutowski-Real entropy. Anything to the right of the Gutowski-Real line, the solution, which is the supersymmetric dual giant, its entropy is given by projecting left. Okay, 0. I'll take one last one. Oh, it's not symmetrical. I'll take one last minute just to make the point. I won't be able to say how and why, but okay. Last point is this. Look, we now have, if you believe our results, a set of 5-parameter set, supersymmetric, an entropy as a function of 5 parameters on the supersymmetric manifold. Now, I want to make contact with all the recent excitement of matching the superconformal index with black holes. Let's review for a minute the logic behind the recent excitement. Supersymmetric indices, some charges along a line, take 4 charges and keep them fixed, and some along a 5th line. Okay? Black holes appear to exist in codimension 1. A line intersects a codimension 1 surface at a point, and so you could try to compare the index, which is associated with a line of charges, with a point in which this line intersects the sheet of supersymmetric black holes. This has had fabulous success, at least when JR is not too large. Okay, just half a minute. Okay, now I'm claiming that there are supersymmetric configurations everywhere along the line, not just on the supersymmetric black hole sheet. So now you must wonder, when should we expect these two to match? Perhaps the index will be maximized somewhere else on the line, not where it intersects the sheet. Now, the index is a sum of contributions with alternating signs. Very hard to keep track of the alternating signs. If you ignore the alternating signs, just choose the local maximum, you find that when JR is not too large, the maximum contribution is extremized on the black hole sheet, but when JR is larger, it's not. So this analysis suggests a phase transition in the index at larger values of JR. We don't have a direct confirmation of this. That's it. I'm done. Okay. So this was
Thank you very much. That was great. Short down.
So like a dual giants corresponds to some kind of superfluid phase in field theory, and so it seems like this like a dual giant dressed black hole corresponds to some kind of two-fluid phase in field theory.
Yeah.
But do you have any intuition of why hydrodynamic modes and superfluid modes do not interact?
Yeah. In the gravity, it's clear. They don't interact because R is very, they're separated in distance. This is a fantastic thing about ADS CFT. Vaguely, what you want to say is that the operators that are turned on have such high dimension that they don't interact with this sea of low dimension stuff. That's the vague field theory intuition for this non-interaction. But this may be only really precise at larger lambda. At lambda of order 1, they may start interacting because locality goes away. I should emphasize that I believe this phase diagram does not change qualitatively as you take lambda away from infinity. Large but finite lambda, same phase diagram. Thank you.
Joaquin.
When you go away from this set of charges where the black holes are supersymmetric, there are also these solutions of Santos with scalar hair.
Yes.
Would this one have more entropy than those? Or?
Yes, yes. Okay, excellent. So there are two things about this, about these solutions of Santos. I'm not sure if I'm allowed to say this. Okay, but the Santos has privately communicated to me, okay, that when you do these solutions more carefully numerically, as you know, the way he computed these solutions is he computed them at finite temperature and then took the temperature to 0. And in his paper, he went down to temperatures of order 10 to the power minus 4 or something like that in natural units. He's now improved the calculation to go down to 10 to the power minus 10. And you see that the entropy, which was steady there, around 10 to the power minus 8, I think, tanks and then appears to go to 0. Okay, so these new solutions do not appear to be smooth supersymmetrically. Okay, so then it's hard to compare. But, okay, fine, let's leave it at that. Yeah.
Okay, maybe since the dinner is getting cold, we will finish here. Let's thank Shiraz again.